Welcome. This is the Cisco CCNA3-ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Welcome. In Module 1, we are looking at the Single Area OSPF v2 concepts. So this video is going to be talking about what OSPF, how does it function, key characteristics, things of that nature. Also looking at OSPF operations in a single area and some packet types. So first of all, let's look at the features and characteristics of OSPF. OSPF is a link state routing protocol that was developed as an alternate to RIP. OSPF is open source. It has significant advantages over other routing protocols such as RIP. The fact that it's a link state routing protocol, that means it will use the concept of areas. A network administrator can divide the network into routing domains, which are more like spheres of control, into distinct areas that help control routing and updating of traffic. A link is an interface on a router and the network segment that connects to routers, or a stub network such as a LAN. The information about the state of a link is known as a link state. Basically, all link state information, including the things like network prefixes, length, and the cost, are shared with other routers. So this module will cover basics on OSPF, specifically on single area OSPF, the implementation, and the configuration. A big takeaway is link state basically means that all routers will have a map, per se, of all other devices on the network. It builds a map for connectivity overall on the overall network. That means if the network changes, a route goes up or a route goes down, all other devices, all other routers have to be sent updates in terms of what the different link states are. So that makes this a little bit more complicated than other routing protocols. But the fact that all routers have a map makes things a little easier too. So it just kind of depends on circumstance and which routing protocol is most appropriate. And we'll get into those a little bit later. Alright, moving on. All routing protocols will share similar components that they use to exchange routing information. So these routing protocol messages that are used to exchange information help to build the data structure of the route maps or the routing information. So routers running OSPF will exchange messages to convey routing information using 5 specific packet types: a hello packet, a database description packet, a link state request packets, a link state update packet, and a link state acknowledgement packets. One thing that I do not like with the new material is it doesn't really give us a nice description of what those packet types are. So the hello packet are packets that are sent over a period of time to all interfaces for the purpose of establishing and maintaining neighbor relationships. Basically, the hello packet are a multicast sent via multicast on the network, having a multicast capability that enables discovery of the neighboring routers dynamically. The database description packet basically is at the time of the adjacency being initialized. When one router learns about a neighboring router, that's the adjacency coming up, these packets are exchanged. The packets are describing the topology of the database content. Basically, what the router knows about the topology. It will put that in a database, send it to its neighbor when there's an adjacency formed. The database may be described by using multiple packets, or not just a single packet, because again, all routers will eventually have all information that all other routers have in a link state, So they do this by exchanging the database description packets. It is important to note that with OSPF, there will be a master router that controls everyone else. And the master router will be known as the master. All other routers will be known as slaves. The database description packet are sent by the slaves after sending the database description packet by the master. So the master will have as complete information as possible, then it will update all the slaves. Next would be the link state request packet. So as a router may find part of its topology database that are out of date, after a database description packet exchange with the neighbors, the link state request packet is utilized for requesting the pieces of the neighborhood database which are more up to date. So essentially it may have pieces A, B, and C, and A and B are up to date. C is out of date. The link state request packet will be sent to say, hey, I need this specific information. Next will be the link state update. And basically the flooding of a link state advertisement is implemented by these packets. It's a collection of link state advertisements and are carried by each link state update packet, one hop further from the origin. So basically a packet may be included by several links being sent. Normally you'd want to send a link state update packet just to your neighbor. So that is the one request past your neighbor. Basically, if you know your neighbor, and your neighbor will share its neighboring information, and its neighboring information will share it, you can slowly build a network map based off of just the update packets. Lastly will be the link state acknowledgement packets. The reliability of flooding link state advertisements is made by explicitly acknowledging the flooded advertisements. The accomplishment of this acknowledgement is done through the sending and receiving of the link state acknowledgement packets. Basically, a single link state acknowledgement packet is used to acknowledge multiple link state advertisements. This is the type of packet that will be sent to understand that I am receiving updates, I'm receiving information, and you will acknowledge it, or the OSPF routing protocol will acknowledge that it received update packets using the acknowledgement packet type. So those are our 5 main types of packets used by OSPF in exchanging information. So one issue is the database description. There's multiple databases. So there's the adjacency database, which has the neighbor table. There's the link state database, the LSDB. This is the topology table. And there is the forwarding database, the routing table. So essentially, if you want to look at the different databases, you have to run a few different commands. We have a lab going through all of this, so we'll do that in Packet Tracer a little bit later. But for now, if you want to view the adjacency database, you would do a show IP OSPF neighbor. If you want to look at the topology table, you will do a show IP OSPF database. If you want to look at the forwarding database, it would be a show IP route command. So each database has different show commands so that you can see different types of data. So the router will build the topology table using results of the calculations based on a shortest path first algorithm, an SPF algorithm. The SPF algorithm creates a tree by placing each router at the root of the tree and calculating the shortest path to each node. The tree is then used to calculate the best routes. And then that's what's actually forwarded. So the link state operation, in order to maintain routing information, it has to complete a generic link state routing process to reach each state of convergence. The state of convergence is going to be where all routers have information on all other routers. There are a few link state routing steps that are completed by a router. Each router will establish neighborhood adjacencies. They will exchange link state advertisements. They will each build a link state database. They will each execute a SPF algorithm. They will each choose the best route. They will also then share that information with their neighbors. And again, this is just a generic link state routing process that each of the routers will go through. Now let's look at, to make OSPF more efficient and scalable, there's a hierarchy routing using areas. We can have a generic single area with OSPF being area 0. We can also have a multi-area called multi-area OSPF. And this OSPF is implemented using multiple areas in a hierarchy fashion. All areas must connect back to the backbone, what's called area 0. Routers interconnecting the areas are referred to as an area border router, ABRs. The focus of this module is only on OSPFv2 using single area. Also, typically getting more in depth with the ABRs is not done at the CCNA level, so do keep that in mind. Just for completeness sake, here we have two other areas. We have area 1 and area 51, and we have two ABR routers, R1 and R2. Again, everything connects back to area 0. The hierarchy topology being looked at here basically allows for smaller routing tables. It will reduce the link state update overhead. Basically, you stay within your area, so area 1 will have its routing updates, area 51 will have its routing updates, and it will also reduce the frequency of the calculations, because again, you're only working within your area. So we were looking at OSPFv2 for the most part. Well, there is an OSPFv3, and that is specifically for IPv6. It will exchange router information to populate the IPv6 routing information with the remote prefixes. Again, note that with OSPFv3, address family features, including support for both IPv4 and 6, are beyond the scope of the CCNA. OSPFv3 has the same functionality as v2, but uses IPv6. So the same type of packets, same type of advertisements and databases, same thing. Same type of SPF, but again using IPv6 information, not IPv4. OSPFv3 has separate processes from its IPv4 counterparts. So you can have OSPFv2 with one process ID, and you can have a OSPFv3 with a separate process ID. The processes and the operations are basically the same, but run independent of one another. Now we have again our OSPF packets. We talked about the hello packet, the database description, link state request, update, and acknowledgement. Here's where we go a little bit more in depth. Generically, the hello packet will be used to discover neighbors and build adjacencies. The DBD will check for database synchronization. The LSRs will request specific information. The LSUs will send specific requests. The LSAs will acknowledge the other packet types. Again, the LSUs will have different types. The different LSAs will also have different types. Again, this is getting outside what you'd normally be needing for the CCNA. This is more CCNP, understanding the types of LSAs. This is more just information for you to have. LSUs are used to forward OSPF routing updates. An LSU packet can contain 11 different types of LSAs. LSUs and LSAs are often used interchangeably, but the correct hierarchy is an LSU packet contains LSA messages. And again, there are 11 different types of LSAs. Common LSAs, LSA 1 is a router LSA. 2 is a checksum for database. 3 or 4 is summarization of LSAs. 5 is the autonomous system external LSAs. 6 is a multicast OSPF LSA. 7 is a defined not so stubby area, and so forth. Again, outside the scope of this exam, this is more just FYI, so that you understand there is a process for the 11 LSAs. The OSPF type 1 packet, the hello packet, are used to discover OSPF neighbors, advertise parameters, and elect a designated router, master router, and a backup designated router. So a designated router, DR, and a BDR on multi-access networks like Ethernet. Point-to-point links do not require a designated router or a backup designated router, but they may happen. OSPF has its own packet header, and it will have things like its router ID, its area ID, if there's authentication, the hello intervals. It will also have the designated router address and the backup designated router, as well as a list of neighbors. OSPF operations. We have 7 states of OSPF. There actually is no video for this. I don't know why it says video. So there are 7 main states: the down state, the initiate state, the two-way, the X-start, the exchange, loading, and full state. The down state, there is the initial default state. Basically the router just turns on. There is no hello packet received, so it's down. The router will then send hello packets, and it will transition to an initiate state. The initiate state basically is when you receive a hello packet from your neighbors. They contain the router ID of the sending router, and this will transition to a two-way state. Before it transitions, it may send an acknowledgement to verify the hello packets. The two-way state allows for communication between two routers bidirectionally, assuming a multi-access link like Ethernet, and they will start electing a designated router and a backup designated router. After they designate a designated router, they will transition to a two-state the two-state will transition to a X-start state method. And that X-start state method will be, the two routers will decide which router will initiate the DBD packet exchange. Again, that's the database. And will then decide upon the initiating BDB packet and the sequence number. They will then exchange information. So the routers exchanging the different database packets will be an exchange state. If additional routing information is required, then they will transition to a loading state after the exchange. If the exchange doesn't need additional information, it will transition to a full state. The loading state will send additional LSRs and LSUs to gain the additional information, and then it will run through the SPF algorithm again before transitioning to a full state. Again, a full state is when the link state database of the router is fully synchronized with all other routers in that area. And that process is how OSPF actually does its convergence throughout the area. So how do we establish a neighbor adjacency? So to determine if there is a neighbor on the link, the routers will send a router ID out all of the OSPF-enabled interfaces using a multicast address. The multicast address 224.0.0.5 is basically used to send out an OSPFv2 packet out those interfaces. The OSPF router ID is used by the OSPF process to uniquely identify each router in the area. The ID is a 32-bit number formatted like an IPv4 address, but is assigned uniquely to each of the devices. You'll notice in the Cisco material, we keep them very simple: 1111, 2222, 3333, and so forth. In the real world, you'll have a documented network map, and you'd have the IDs laid out appropriately. When a neighboring OSPF-enabled router will receive a hello packet, it will look at the router ID, and if it's not within the neighborhood list, the receiving router will attempt to establish a new adjacency. The routers have to have adjacencies formed to be able to share information. There are a few different steps when we are looking at forming those adjacencies. Down to the initiate state, looking at OSPFv2. Basically, OSPF2 is enabled on the interface. The transition from down to the initiate state will start sending once there's a hello packet on a interface. If there is no hello packet sent or received, it will not be able to discover neighbors. That hello packet is what's used to discover those neighbors. That will transition to an initiate state once the neighbor router receives the hello. So if we have router 1 learning about router 2, router 1 will send router 2 a hello packet. Router 2 will transition to an initiate state because it received a hello packet from R1 containing R1's router ID. R1 will then receive R2's hello packet and will notice the message will contain the router 1 ID in the list of information that R2's neighbors has. So now R1 will add R2's router ID to the neighbored list and will transition to a two-way state. If R1 and R2 are connected with a point-to-point, they transition to a XStart. Realistically, that's only used for point-to-point. If R1 and R2 are connected over a Ethernet, they will start forming a designate route and a backup designate route election, seeing who will become the master. The DR and BDR elections occur where the router with the highest router ID or the highest priority is elected as the designated router. The second highest will become the backup designated router. Again, here we're looking at the highest router ID will become the designated router or master. After the two-way state is enabled, the router will transition to a database synchronous state. Basically, this is where there are 3 steps that will occur to actually transition and sync database information. Basically, first, the first router will, the highest router ID, whatever the master router is, it will send the database DVD first. They will exchange DVDs as many times as needed to convey the appropriate updated information within the database. The other routers must then acknowledge each DVD with a LS acknowledgement packet. They will then send all slaves routers will send a LSR to each other, collecting the DVD information and storing it locally. As information is found to be missing, it will send up LSUs as a update request. And again, acknowledgement sent once all the information is then brought together. After all LSRs have been exchanged and satisfied, the routers are considered synchronized in a full state, and then there might be a update sent if there is any changing information. If not, every 30 minutes just to verify. This is when we would say that it is converged. all routers have all information on all other routers. So a question that I often get is, why have DRs? Why have that designated router? Why have that master? So when we're dealing with a multi-access network, they can create challenges for OSPF regarding the flooding of LSAs. The creation of those multiple adjacencies can cause issues. So Ethernet networks could potentially interconnect many OSPF routers over a common link, creating adjacencies where every router would lead to an excessive number of LSA exchanges, basically flooding the adjacencies. So a common formula is the number of adjacencies is equal to n, which is the number of routers, times n minus 1, all divided by 2. There are 5 routers, so you can actually have 5 times 4, that's 20, we divided that by 2. That means there are 10 adjacencies. This flooding can be very excessive. So, with a DR, we can control some of that flooding. So LSA flooding with a DR, as increasing the numbers of routers on a multi-access network also increases the number of LSA exchanges between the router, the flooding then also increases. So if every router in a multi-access network had to flood with acknowledgements, you would start seeing a flood of those updates, and that uses bandwidth, and that would just create issues. So OSPF elects a DR. The DR will be used to collect and will also be used as a distribution point for LSAs. Basically, it will be sending and receiving them. The backup DR is also elected in case of a DR failure. All other routers will become DR others. Basically, a third option. Basically, if the DR fails, the BDR becomes primary, and then they'll hold another election for a new BDR. The BDR is the only used for dissemination of LSAs. The router will still use the best next hop router indicated in the routing table, but the BR will actually be used to disseminate the router updates that will be used. And that is the end of this chapter. One thing that I want to point out is this chapter went really in depth with OSPF, and realistically a lot of that information is more commonly found in the CCNP. Understanding the election of the DR is important at the CCNA level. There is a process that it uses. How it actually elects them typically is not done at the CCNA level, it's done at the CCNP level. But you need to understand that there is a process. What the process is, not so much. If you have any questions or concerns, please reach out and let me know. Thank you.